Good afternoon again, Evan Stamon here for 1.4 Making a Difference. We are looking at the fourth lesson on Euclidean geometry for grade 12, and we are now looking at equiangular triangles are similar. Now this is again one of my frustrations that I have with education. We tell you things are true in the junior grades, but we never prove it to you until much later in your school career. And in grade 9, we told you that similar triangles had equal angles, or that triangles that had equal angles were similar, but we never took the trouble to ever prove it to you. And what we're going to do today is actually get around to that proof. So what I'm saying is that if I have two triangles where I know that these things were equal to one another, let's just quickly get that colored in, and I had another triangle, which as we saw in a previous slide, I said that these ones were equal to each other respectively, A, B, and C, D, E, and F. We said we knew in grade 9 it must follow that triangle ABC was similar to triangle, in this case, let's again make sure, A goes with D, B goes with F, and C goes with E, angle, angle, angle. And we said importantly, and this is the key point I'm making now, is we said we then knew that this led to the idea that these sides were in proportion. And which sides, again, we said the whole point of writing this thing in order was so that we could see that AB, the first pair, would be going with DF, that the second pair, ABC, would be paired with FE, and that the outer pair, AC, would be paired with DE. Now, again, that connection between that the angles were equal, leading to the sides being in proportion, is something that we accepted in grade 9, but we never ever got around to proving. And again, it's such an important proof that actually it is the second proof that you need to know as bookwork for your matric syllabus. And it's actually a bit of a cheap and cheesy proof because we're going to use a key skill of Euclidean geometry, which is to use prior work. So if I've got A, the top here, let's just keep it the same as previously, B and C, and D, E, and F, and I've marked it such that these triangles are similar, equiangular in this case, so triangle ABC is similar to triangle DEF. This is what I have been given. Remember, we spoke about formal proofs having these three situations. Then what I'm required to prove is that proportion statement, which is that AB over DE equals AC over DF. Now, I'm leaving it blank for the moment, and again, I'll use a little bit of a cheat to include the third part, that BC over EF. Again, we spoke about it earlier, there's often a construction, and again, I'm going to use quite a crafty one. You see, the whole point of Euclidean geometry is Euclid set out to explain the entire world's basis of geometrical knowledge by saying if you accept the first theorem, you have to accept the 1000th theorem. So the 1000th theorem is based on the 999th theorem, which is in turn based on the 998th theorem. So this theorem, which we are going to use today on equiangular triangles being similar, will be based on the proportion theorem. And so all I need to do is make this situation look like the previous situation. Now, how is this situation different from the previous situation? Well, if you think about it, here I've got two separate triangles. They are not overlapping one another. Whereas in the previous proportion theorem, I had something that looked probably something similar to that. One triangle embedded inside another triangle. And so the skill here is to make this new situation look like the old situation. And so what I'm going to do is I'm going to place point G on DE such that AB equals DG. So I'm putting G here somewhere such that this piece of line is equal to this piece of line. I'm going to do the exact same thing on the right-hand side. I'm going to place H on DF such that AC equals DH. So again, H is going to be here somewhere such that AC equals DH. And what I'm going to do is I'm going to join GH. Now, by joining GH, I've now created a situation where this right-hand triangle, the one that's now almost in the middle of the page, looks very similar to the proportion theorem of previously. The problem that I have here is that I don't know if these lines are parallel. So what I'm now going to do is I'm going to move on to the proof section of my situation, and that is to realize that these two triangles that I've drawn here are actually congruent to one another. This triangle and the top triangle here are going to be congruent to one another. Why, you might ask? Well, I need 3 facts, and so far I've been given 2. And so I'm going to look at it as follows. In triangle ABC and triangle DGH, 1, AB equals DG, construction. 2, AC equals DH, construction. And I need a third fact, which is either side or an angle. But since I know nothing about the length of GH, I'm going to move on to looking for an angle. And I need to look at the included angle. And we know that A equals angle D because it was given to us that the triangles were similar. Which means that we now know that these two triangles are actually not just similar to one another, but actually are congruent to one another. So triangle ABC is congruent to triangle DGH. Again, look at that symbol. 3 horizontal stripes. 2 horizontal stripes would have been equal. 3 horizontal stripes, it is very equal. It is equal in every respect. So all the angles are equal and all the sides are equal, respectively, in the 2 triangles. We need a reason for congruency, and in this case, the reason is that side angle, side. 2 sides and the included angle, because we know that this angle equals this angle. But what follows from this argument is therefore, it must follow that therefore angle B must equal DGH, because the triangles are congruent. So however big this angle was here, we know that it must be the same size as that angle because of congruency. But we knew from the first statement that B equaled E because it was given that the other 2 triangles were similar. But if these 2 angles are now equal to one another, so if B equals the angle at G and B equals the angle at E, it must follow that the angle at G, angle DGH, equals angle E, because they have B in common, and therefore it must follow that GH is parallel to EF, because the corresponding angles of this pair of triangles are equal. And if we now have a situation where if the lines are parallel, we now have a situation where we have the proportion theorem. We have a triangle cut by a parallel line. Therefore, it must follow that DC to DE equals DH to DF. And running out of space a little bit here, I do apologize, but we will move it up a little bit and we will get the final statement here, which is that therefore since we know that DC is the same length as AB, therefore AB to DE equals AC to DF, and we have proven what we had set out to prove. Okay, so again, this is one of the important theorems that you need to know. It's one of the two theorems that you need to know pretty much off by heart. They have asked a piece of theory in every exam, in every final exam that I've seen for the last however many years, even since I wrote matric exams 30 odd years ago. You know that there will be 5 marks on this. You can waste those 5 marks, or you can simply sit down and learn your 6 theorems pretty much off by heart and guarantee yourself those marks. Okay, so we now know that triangles that are similar, that do not overlap one another, but if we can prove that their angles are equal, that they are equiangular, using the technical term, means that their sides are in proportion. And this is now probably the key question that they're going to ask from this chapter in the matric exams. So here is a fairly friendly example. It's not too complicated, but it does come from the Siavula textbook. And you're told that you've got 4 points on the circumference of a circle. I've got little alarm bells going off in my head because as soon as I hear the 4 points on the circumference of a circle, I'm thinking certain key terminology. Are you thinking it with me? Hopefully you've recognized that that means that PQST must be a cyclic quad. TS is produced, so simply elongated, made longer, to V, such that SV equals 2TS. So SV equals 2TS. So again, like I said to you before, I'm going to mark my information on the diagram. So I'm going to mark that orange statement over here. SV is twice as long as TS. So I know that that length there is in the ratio of 2:1. And I'm told that TRQ is produced to U such that VU is parallel. Okay, I can see that VU is parallel to SRP. So I can see that these two are parallel. And again, reminding you that that makes me want to think not so much of corresponding cointerior and alternate angles, but now that sides are going to be in proportion. It's not to forget the grade 8 stuff. It's to say that I now need to also have a higher thought in mind, and that is that the sides are going to be in proportion. Okay, question A. Given all this information, can I realize that TR over RU equals 1/3? Well, we've spoken about this for quite a couple of times in the past couple of lectures, that if I've got 2 pieces in the ratio of 1:2, part to part, I should also be able to realize that I have a part to whole situation. So if I know that SV to TS is in the ratio of 2:1, I should also know that SV to TV is going to be in the ratio of 2:3, or that TST to TV is going to be in the ratio of 1:3. So please don't forget that if I have parts to part, I can also therefore realize parts to whole. Okay, now that 1:3, that ratio on the far right hand side there of 1:3, again, we spoke about this previously, that I should be able to realize that a ratio of 1:3 is the same as a fraction of 1/3. So this is in the background thinking of how I'm approaching this sum. Given that proportion, that those two side lengths are being in the proportion 1:2, I realize that there's a part to part of 1:2, or 2:1 in this case, which leads to a part to whole of 2:3, or 1:3. But the ratio 1:3 is the same as the fraction 1/3. Now, having rewritten that in that format over here that I've done so on the right hand side here, that leads me to think, well, hold on, that's the same as that fraction there, 1/3, 1/3. So let's think this thing through. Question A, TR to RU is that line to that entire length over there. It's been cut by that parallel line. Yes, admittedly, the parallel line's been written, the marker's been written out there, but I could just as easily have written it over there. And as a result, we can see that TR over RU is going to be the same as TS over SV, sorry, TR over RU